All right, let's dive right into this explainer. And we're going to start by addressing a pretty fascinating misconception about the outermost layer protecting our central nervous system. For a long time, the dura mater has been thought of as just a simple physical shrink wrap, something that's just there to keep our brain and spinal cord safe. But today, we're going to completely dismantle that idea.
The term dura mater is famous in the medical world, for sure. But historically, an anonymous ancient Muslim scientist actually described the meninges as al-Damag, which beautifully translates to the mother of the brain. And honestly, this name hits the nail on the head, because rather than being just a tough, inactive barrier, the mother of the brain is a dynamic, highly vascularized, and deeply complex living tissue that is constantly interacting with the nervous system it protects.
So here's our roadmap for this explainer. First, more than a wrapper. 2, inside the cranial dura. 3, the spinal dural sac. 4, nerve root cuffs. And finally, number 5, discovering the telocyte. Okay, section 1, more than a wrapper, beyond a physical cover. Let's kick off this journey by tearing down the whole idea that the dura mater is just some passive barrier.
Here's why this absolutely matters. Understanding the normal, intricate structure of the dura is quite literally the foundation for surgeons and pathologists who are trying to treat major medical emergencies. Whether a neurosurgeon is performing a duroplasty to repair a cerebral fluid leak, or a radiologist is trying to diagnose an intracranial hemorrhage or meningitis, they have to intimately know the microanatomy of this tissue. I mean, you can't fix the mother of the brain if you don't know how she's built, right?
Moving on to section 2, inside the cranial dura, the brain's tough shield. Now, moving inward, let's look directly at this layer resting immediately inside your skull.
What is genuinely mind-blowing here is that this incredibly dense protective layer is shockingly thin. In humans, it measures just 564 micrometers thick on average. To put that into perspective, that's roughly half a millimeter. Yet, within that microscopic thickness, an immense amount of biological architecture is taking place. Despite being a fraction of a millimeter thick, it somehow crams in 3 distinct continuous layers. You've got the outer periosteal layer facing the bone, the middle meningeal layer, which is highly cellular, and the inner dural border cell layer, or DBC for short. These layers are woven together with collagen bundles and elastic fibers to give it both extreme tensile strength and just a little bit of flexibility. If you look at the top of this diagram, notice how the outer periosteal layer is firmly attached to the skull bone, especially at those suture lines. Because of this firm, biological glue, you actually don't have a natural epidural space in your head. It's only what we call a potential space. If there's a trauma and bleeding occurs, the blood literally has to pry and tear this layer away from the skull. And that is exactly why a cranial epidural hematoma appears short, wide, and lenticular on an MRI. Let's see how this builds when we look at the deepest layer, the dural border cell or DBC layer. Clinically, why this matters so much is that this innermost layer completely lacks strong collagen fibers. Instead, it has these wide extracellular spaces filled with proteoglycan. This makes it an inherent structural weak point. During a head trauma, this is the exact layer that easily tears apart, causing a subdural hematoma. Because it lacks those anchoring collagen bundles, the bleeding just dissects this plane freely, creating that classic long, thin crescent shape you see on brain imaging. All right, section 3, the spinal dural sac, a protective spinal tube. Traveling down past the base of the skull, the anatomical story completely changes. Just notice the stark contrast here. Unlike the cranial dura we were just looking at, the spinal dura actually drops its outer layer entirely. It totally loses the periosteal layer once it passes the foramen magnum. And by dropping that outermost layer, it's no longer glued to the bone. This creates a brand new natural gap between the dura and the vertebral bone, an actual anatomical epidural space filled with protective fat. Looking right here at this diagram, you can clearly see that newly created, fat-filled epidural space on the right. This structural change is precisely why spinal epidural anesthesia works during childbirth or lower body surgery. Doctors are utilizing this exact anatomical gap. Plus, this adipose tissue, along with the spinal dura's specific blend of collagen and elastic fibers, acts as a dynamic cushion. It protects your spinal cord from stretching and compressing forces every single time you bend, twist, or change your posture. And honestly, this is pretty wild. Science is still uncovering the secrets of this region. Researchers have recently discovered previously unknown dural venous sinuses hiding right there in the lower back, specifically between the L5 and S1 vertebrae in adult cadaveric specimens. This just proves our foundational anatomical maps are still being updated, and there's still so much to learn about how blood flows through the spinal cord's protective layers.
Section 4, nerve root cuffs, where nerves exit. Zooming in a bit closer, we hit the exact delicate points where peripheral nerves punch through the spinal dura to exit out to the rest of your body. Historically, these nerve exits have been called dural sleeves, which is, well, somewhat inaccurate. As you can see in this transverse section, they aren't just simple sleeves at all. They're actually incredibly complex, double-layered wraps of tissue. As the nerve exits, it gets wrapped in a fibrous dural component on the outside and a cellular leptomeningeal component on the inside. Think about it. To protect the fragile exiting nerve from the harsh mechanics of your moving spine, the body creates this elaborate, shock-absorbing system. The outer fibrous layer is about 150 microns thick, but what's amazing is that its collagen lamellae are separated by micropads of adipose tissue, literally tiny cushions of fat. Inside that is a cellular layer, a mere 5 to 8 microns thick, made of roughly 14 tightly bound cellular strata joined by tight junctions to form a barrier. It's just a microscopic marvel of engineering designed entirely to protect your peripheral nerves.
And finally, Section 5, discovering the telocyte, a new cellular inhabitant. For our last stop today, let's zoom all the way down, past the tissues, down to the extreme microscopic level, to look at a recently discovered cell. I want to introduce you all to telocytes. These are special interstitial stromal cells that, believe it or not, were completely unknown to science until 2005. Because their branches are incredibly thin, they're entirely invisible to routine lab stains like H&E. They were only first spotted in the cranial meninges in 2012, and it wasn't even until 2015 that transmission electron microscopes finally proved they existed in the spinal dura mater as well. Just take a look at these fascinating structures. Over on the left is a diagram showing their theoretical string of beads structure. They have a really small cell body and extremely long prolongations called telopodes, which feature alternating dilations and thin segments, podoms and podomers. And on the right, that is the actual transmission electron microscope proof of these alien-looking cells hanging out inside the dura mater. You can actually see those massive, long arms stretching out through the collagen fibers. So, what do? We are really just beginning to understand them, but we do know that act as microscopic communication networks. They participate in tissue regeneration. They literally nurse and guide precursor cells by releasing tiny biological packages, things like exosomes and ectosomes, right into the surrounding tissue. They are essentially the hidden microscopic directors of tissue health, living right inside the mother of the brain. Which leaves us with a truly fascinating thought. The dura mater is something we've been cutting into and studying for literally centuries. Yet, we are still finding entirely new structures like lumbosacral venous sinuses and entirely new cells like telocytes that manage regeneration. If we're still discovering fundamentally new biology inside the mother of the brain today, what other incredible secrets are hiding inside your anatomy right now, just waiting for the right microscope to find them?